welcome. It's our last Wednesday together. I'll have a countdown for every last day that we have. It's our last Wednesday together, if you can believe that. Before we get started, I keep forgetting to mention it in my classes, all of them. So now I'm being really strict with myself, because if you go to your Moodle page, oh, I guess it's not started, but if you go to your Moodle page, then on the side, you should have a formative evaluation of college professor tab. So, and that's where you give me a grade, basically. It says it's going to take 25 minutes. I don't see how it could possibly take you 25 minutes. But what you do is you go in here and, well, you read the instructions, and then here's where it says it's going to take approximately 25 minutes. Here's the reason I'm panicking, is because they're due on Friday. So we're not going to use any class time, because I feel like that's kind of a waste of our time together. I know. As a student, you want to waste time together. But for me, in the last week of classes, no, I don't want to do that. So you go to the survey link for the fall of 2021. And then you read the instructions, and then you hit next. And then you're going to choose, and you might be doing these for more than one class, right? So you might have already done these, probably, but you would find our class. All my friends are on this list. So fun. Anyways, here we go. There's me. Okay. And then you would select which class you're in. Of course, you're in Data Science 300. And if you're in Stat 230, for example, then you could do that one as well. But I'll remind those guys tomorrow. Okay? And same with Stat 240 if you're in 240, but no. Okay, so anyway, so then once you select a class, then you'll be able to submit the results. I guess I could try and see what it looks like. Next. Okay, so the thing that I care about is these kind of the ratings. Okay, so the first block of questions, those are the most important ones. And I mean, wow, so many questions. And then there's these boxes where you can fill in answers. Only if you feel like you have something to say. You don't have to fill in those boxes, because that can be the time-consuming part. Okay, so just focus on if you could do those strongly agree to strongly disagree or not applicable ones, that would be great. And then the dean's office will be happy. Okay, so so if you can do that, that would be awesome, and I appreciate it. Anyways, I used to be on top of things with those evaluations, because it's how we would get work. And so, or not how, but we'd have to submit them when we apply for more work and stuff like that. But now I'm too old, and I don't know, I don't care as much. So here we go. I'll put that as a reminder. I'm also going to send out an announcement. I'm just curious though, are you guys getting emails from the college to tell you to do these evaluations, or is it all on me to tell you about them and to get you to do them? That's what I don't know. I've been assuming that the college sends out emails to you guys, nagging you to do it. Probably. Right. So I'm curious. All right. Till I hear back. maybe someone knows if you've gotten emails about it. So please do my evaluation. Whee! It closes Friday. Oops. Friday, December 3rd. What's also due Friday? Your last assignment, right? Assignment 8. Well, it's not your last assignment. You've got your final project as well. Decided not to do an assignment for chapter 9 because you guys are completely overloaded anyways. So we're not going to do an assignment for chapter 9, but there will be the possibility of showing off your chapter 9 skills in the final project. Okay, so assignment for chapter 8 due on Friday at 11:59 PST. Actually don't know the time that this thing closes, the evaluation, so maybe I'll fill in after. Okay, so the assignment for chapter 8 is due on Friday. Okay. And quiz number 4. The thing about the end of term is it is very stressful, right? As a student, also as a teacher, but as a student, it's very stressful because everything is just piling up, right? But on the plus side, once you're done with it, you're done with it. That's all there is, right? And so you have to kind of get through it, and then you'll make it to the other side, I promise. Quiz number 4 opens on Friday. I set it to open at 9, but Friday, pretty sure I set it at 9, and closes on Sunday at 23:59 PST, of course, as always. Okay. Same thing as the other quizzes, 20 questions, multiple choice, 50 minutes, and that's it. Okay. And it's on chapters. Whoa, dropped my pencil somehow. I'm not sure how it went down, but it did. And it's on chapters 8 and 9 only. Okay. So one other thing that I'm curious about is we're supposed to meet on Monday, but I'll be, well, it's weird because I'll be in the Okanagan, so I'll be in Kelowna, which I'm usually not, right? I'm usually in Edmonton, but so I'll be in Kelowna, but I don't really have a designated workspace, so I'm not sure if it's going to be the best kind of lecture environment or kind of meeting environment. I don't really know what my setup will be there. So what I was thinking of doing is making a video where I talk about the final project and everything like that. And then we can set up a different day during the final exam time where you can have some drop-in time where you ask questions. Okay, so that's what I'm kind of proposing. Unless you really want to meet on Monday, then of course I'll make that happen. But like I said, I don't know what my setup will be, so I was thinking this might be easier. But anyways, I think you guys are all in data science. You guys don't have a ton of final exams per se, but you do have a lot of projects. If you know of a day that would work, that I should be available for questions for the final project, then throw that in the chat. The final project, I haven't posted it yet because you guys are going to be, you guys have enough to deal with. And also I want to just do a run through, another run through where I can make sure that everything's good. Final project will be due December 15th. I will have a day, probably, let me see here, December 15th is a Wednesday. So probably like December 10th. No, maybe the 13th. Let's do it on the Monday. I will be available for drop-in questions on December 13th. Okay. So if there's something that you're working on and because I want to give you enough time to develop questions, otherwise it doesn't really help to be able to ask me questions if you haven't worked on it enough. So I'll be available for drop-in questions on December 13th in our Zoom room. Okay. All right. So I feel like that's it. That's a lot. That's it for stuff I wanted to put out there. And what I'll do, because there's not a lot of us here, I know you guys are swamped, I'll send out an announcement with kind of the key things. Okay. So continuing from last day, right, we were talking about classification trees. Right. Let me go back there in my mind. Oh yeah, okay, so we were talking about so classification and regression trees, and we looked at an example. So we introduced last day, we introduced classification and regression trees. Yeah. And we focused on classification trees, right, where we establish cutoff rules, right, or we establish classification rules that allow us to break up the data until it's all the zeros are in one lump, all the ones are in one lump, all the zeros are in one lumps, and so on and so forth. So we started here. Okay. And you're not going to be using any trees in your final project, but one of the options that you'll have is doing a logistic regression. So I do want to go through a logistic a regression example in R, or sort of in R. I posted the notes because that way I can kind of circle stuff as I go instead of just typing it out. And I don't know why I forgot, but I forgot to post the RMD file until right before class. So it's on Moodle, the RMD file, as well as the PDF, which I'll be running through. Okay, so in terms of this last section, 9.5, we're just going to talk about it briefly. You have all the information here, but just kind of what's the big idea here. Okay, and so for regression trees, the idea is that for classification, we develop these rules, right, that split the data until we can't split it anymore, right? And so we develop these rules, which we show as nodes. Okay, so here's a node. Oh. Okay. And then we have branches off of these nodes, and the entire thing is a tree. Okay. So this is off of our training data, right? And so we see that problem that we've seen before, right? Where we have our training data and we build our models and we do everything on our training data. But then when we take that model and we apply it to our validation set, all of a sudden it doesn't perform as well, right? Because it's new data that it hasn't seen before, right? So here, when we have zero impurity, we talked about impurity last day, where, okay, so all the zeros satisfy this, or all of these zeros satisfy being less than 0.0555 as a proportion of dollar signs in an email. Remember, we're talking about spam emails in this case. And so less than goes on the left-hand side. Oops. And greater than, pretty sure, or equal to goes down the right-hand branch. And that's the same for all of these branches. Okay, so we looked at the proportion of dollar signs and the proportion of exclamation marks. If there are fewer than 0.0555 dollar signs, there were 28 of those, then we check for exclamation marks. Right? If there's fewer than 0.07335, then we classify them as zeros because 21 of those were all zeros, and now there's zero impurity here because they are all of the same class, right? Zero. We had to go a little bit deeper, or a lot deeper, to classify the ones and tease out the ones from the zeros. Okay, so these branches are a little bit longer, and then same thing for if there are more than 0.0555 as a proportion of dollar signs. Then if there are more than 0.0615 exclamation points, then we classify those as a 1 because 14 of those, they're all ones. And they all just, we've been able to capture all that information by those two branches. Okay. So it's another way of classifying data, and also we can use it for numerical data as well, regression. But I find that the classification is a little bit easier to wrap our heads around. Okay, so we'll pick up there because I can't remember. Let me just check and see what did I feel like I ended here, the pruning, but let me just check. Yeah, maybe a little bit more. Okay, copy. Oh, and yeah, sorry, there's another thing I wanted to bring in here. A thing. Copy. Okay. Oh, I don't know what I did there, but I hit something. Okay. What we're seeing here, right, is that it's always possible to tease out our zeros and ones in our training data set, right? But that doesn't mean that that's going to apply in our full model or our validation set, right? And so here, if we look closer, we can visualize that same tree in a scatter plot. And maybe that's easier, maybe it's not, okay? But the blue dots here are not spam and the red dots are all spam. Okay, so we've got that class situation in well, they're not dots in the triangles and the squares. Hey, isn't that like the cereal? Is it or sorry, it's not a triangle. It's a diamond or a square. They're the same, but one's on an angle. Okay, and so here, if we have exclamation marks, and remember that first cutoff was 0.0555 something. Somewhere here, sorry. Right, and then what did we say after that? I think we went down to the dollar. So our first cutoff was that the dollar the $0.0555. That'll make more sense. Just trying to make it match here. But 0.05555, this is the equivalent of the first node, right? And so if you're less than here, then you're in one group. And then if you're greater than here, then you're in another group, right? And we can see that a lot of these are spam here. So we've been able to capture a lot of that spam just in that one partition, right? And then because we have one or potentially more not spams in there, so then we add another partition, and that would be the same as doing the exclamation of 0.0615. And then we see that there are 14 ones, and they're all contained in that little region, or I guess it's a big region. 0.06, this one. Okay, so then if we count here, we should have 14 spam points. One thing that I do want to point out is it doesn't look like it makes sense, but 28 of the observations are distinct, and 18 of them, that's where it is. And 18 of them are not spam. Oops. So there's 18 overlapping there. So you can count that one dot as 18. And then there's another 2 observations that are spam that have, so there's 2 observations here. Those coordinates. Okay. Or is it, oh, sorry. X is 0. Must be here. Yeah, those 2. Okay. This tree, or sorry, this scatter plot, I don't know, lost my words. This scatter plot is showing the same information as the tree that we saw up above, right? And so notice the scatter plot holds the same information. As the tree. It's just another way of visualizing it. It's just another way to visualize the classification. Classification. I find that it's a little bit easier here because if we have a new point that we're trying to classify, then you can plot it here and you can see which region it's in, and then you'll know what the classification for that point would be, right? Whether that's right or wrong, we don't know, right? But one thing that we've seen here is that when we have all the little groups, they're all being classified and they're being classified perfectly. That's the equivalent of overfitting our model, right? We've taken too much of the training data information and baked it into our classification, which means it's not going to apply well when we take new data or bring in new data. So what we do is we do some pruning. Okay. So we can prune the data, and we do that backwards. Okay, so we prune the classification tree by removing decision nodes in the reverse order in which they were added. And so you might have noticed that we number the nodes. Okay, so here we had node number 1, it was added first, of course, and then number 2, and then we had number 3, and then we had number 4, and then we had number 5, and then we had number 6, and then we had number 7. Okay, and so if we were to prune this, we would start at node number 7. So what we would do is you'd basically just kind of lump these guys all up, okay? And you would say, okay, well, for node number 7 here, instead of having this this rule that, okay, if it's less than 0.5605, then exclamation points, then you're going to be in class 1. If it's more than that, then you're going to be in class 0. Okay. Instead of saying that, we're going to look at, well, 2 out of the 3 were 1s. So how about just if you find yourself heading down this path, then you're going to be classified as a 1 because the majority of these points were 1. Right? So we introduced some error. There's impurity here, right? Because 2 were 1s and 1 was a 0, right? And so 2 were 1s and 1 was 0. That's confusing. Anyways, so context helps, right? But so we're introducing some impurity here, but it's enough that we are able to apply it to a new set of data, and maybe it'll perform a little bit better than this rigorous set of rules. Okay. Yeah. So like I said here, if we look at the pruned tree here, it's going to be classified as class 1, right? Because 2 of the 3 were in class 1. Because 2 out of 3 were class 1. Okay. There. The reason we do it is because if we have a look at here, okay, so if we consider just one decision node, well, let's take a step back and have 0 nodes. So no partitioning is happening here. And I just say, okay, you're going to be in the class that's most frequently occurring. Then we're going to be wrong some percentage of the time, right? And so, and it turns out that it would be 43.5% of the time in this data set, okay? And so then we introduce 1 node and we say, okay, well, with 1 node, then my classification error is 8.7, okay, which is pretty good. It seems to be holding steady at 8.7, and then it decreases to 6.5. So that's an improvement, right? Because we've decreased the classification error, and then we go to 4.3 and then 2.2. And then what we've seen is at 7 nodes, we have 0 impurity. right? So we're able to perfectly classify all of these zeros and ones. Great. Okay. But then when we apply it to the validation set, so now we're giving it new data that we didn't build these partitions from, and we're applying those same partitions and seeing what our classification error would be. With 0 nodes, it's 39.4. Okay, so that's our jumping off point. And then we go to 20.9 with just the 1 node. Okay, and then it holds steady at 20.9. And then what's kind of weird is it goes up to 21.3, which means that adding more nodes actually gives us more classification error. So that's bad, right? And so here, right, we see that as soon as we introduce 1 node, we've hit the minimized classification error, right? And so here, at 1 node, we have minimized the classification error. Okay. Which means that our final pruned tree would be just the first node. Okay. Therefore, our pruned tree would just be the first node. So very simple. You know, we made it harder because we needed to have something to compare it to. But then in this case, we were able to get away with just the first node. That initial split of the proportion of dollar signs, I think it's dollar signs, let me check. Yep. Maybe I can show that. Right, that first split, if there's less than 0.055 dollar signs, then it is gonna be 21 class 0. And if there are more than 0.0555 dollar signs, then it's going to be in class 1. How did I find that? Well, because the majority here were 21 were zeros, and then 3, and then, so that's 24 out of 28 were zeros. Yeah. It's a lot of zeros, right? And then same thing here, 14 and 3, 17 out of 18 were ones. Yeah. Okay. Good. Maybe what I'll do is oh, I wonder. Okay. How would I? So it becomes 1. Once I prune this up, that's going to be a 0, right? That was my 6th node. My 5th node, if I prune this up, then I have 1 0 and 3 1s. So this is going to be a 1. Okay. And then my 4th one, I have 4 zeros and 3 1s. So then I'm going to have this become a 0. And then here I have 4 1s and 14 1s. So this is going to become a 1. And here I have zeros and zeros. This 0 has impurity. This one does not. But if I combine them, then I have 28 zeros. Okay. So this here is our final pruned tree. With one node. Okay, good. We can do the same thing with numerical variables, but instead of being able to look at it and decide on impurity, right, based off of zeros and ones, which is, I think, kind of intuitive, right? If I tell you, oh, there's a mix of zeros and ones in here, is that a pure mix? No. So then, so there's some impurity there, right? Whereas when we're talking about numerical data, we don't have that classification, right? Because we're not talking about zeros and ones. Now we're talking about measurements, and measurements are on a continuous scale. And so the difference here is that the impurity is going to be measured by the variance within each group. Okay, so let me see if I can find that here. The only differences are how impurity of the partitions is measured. Okay. That's not the part, well, I guess that's fine. I'll highlight the rest of it. But in a regression tree, the impurity of a partition is based on the variance of the outcome value for the observations in the group. Okay, and so so that's a little bit different, right? We want to minimize the variance within within each group that we create, right? And then we split based off of what's going to minimize the variance. So what's going to keep the values that are close together as much as possible. Okay. Now it's a little bit, I think, a little bit trickier, but we can visualize it in the same way if we have numerical data as we did with, or a similar way as we did with classifications. Okay. And so here, I think there's an example. We were looking at, oh yeah, we talked about this example last day. Sorry to reintroduce it here. But we're trying to predict, I want to say, the average in their bank account, or how much they had in their bank account. I'd have to go back and read the example, but let's just look at this visualization. I'm pretty sure that we're predicting the amount that they have in their bank account. And we want to look at, did they default on their loan, yes or no, and what their age is, right? And so here we have kind of amounts, right? And notice that once we have a categorical variable or a binary variable here, then of course all our dots are going to be at 0 or 1, right? Notice that there are no dots in between here because there are no options. You either defaulted on your loan or you did not, right? And so there are no dots in between here, but that's a nice partition, right? That's a first partition. So the first partition here is if it's less than 0.5, then you're in one group, and if it's more than 0.5, then you're in another group. Okay. And then we partition based off of the age. So the second partition happened here. So if you are younger than some age, I can't really tell, 33 maybe, then you're in this one group. Okay. And then we keep partitioning. Remember that once you've made this initial split, then you're working on both sides, right? Because that's the first node in your tree, and then you're working your way down. And so let's focus on the predictions now here. this prediction is the average of 49 and 123. So 49, let me just confirm, plus 123 divided by 2 is 86. Plus 123 divided by 2 is 86. Okay, so the prediction, so the predicted outcome here is the average of the outcomes that are in there. That's basically the same as the classification, right? Because we just took basically the average of the classes, right? Zeros and ones, how many were there? If there were more ones, we made it a 1. If there were fewer ones than zeros, then we made it a 0, right? So basically the same idea, but now we have numerical data that we actually can calculate stuff on. Okay, and notice that if there's only one observation, then that observation is the prediction, right? But I just wanted to highlight that that's how we do it. Okay? And so these partitions are made to minimize the distance between the points, right? So we partition here because the 671 is all on its lonesome, okay? And then there's this group, and they are looking pretty similar. So then we take the average of their accounts, and that's our prediction. And then these two are pretty similar, so we lump them together, and we take the average of those accounts, and that's our prediction. Same thing down here, but they're in another group, right? Because they did not default on their loan, right? The loan default is no for those guys. Okay. Okay. I'm just gonna run through quickly ensemble methods, which is exactly what it sounds like. It's a collection of methods. So instead of just running one regression tree or one classification tree, then what if we did many, right? And then our prediction is not just the outcome of one tree, it's going to be the outcome of an ensemble of trees. Okay. So our prediction will no longer be based off of or based on a single tree. It will now be the ensemble, the collection, or it will now be, what do they call it? Sorry, I'm trying to remember the word. I guess it's going to be the average. It will now be the average prediction of many trees or models, but let's focus on trees. Okay. So we generate a collection of models, and instead of just basing our prediction off of one model, which was what we were just talking about, then we say, okay, well, what if I do this again, right? Remember, we're building these on training data. And so what if I collect a new set, a new random sample of training data, and I figure out how well my model does, and then what my predictions would be, and then I use that and I take the average of all those predictions. Okay. So what we do in an ensemble approach, we develop a committee of individual base models. Okay, so you have these models and you collect random samples and you apply these models. Okay, and then the combination of these predictions are going to form some composite prediction. Okay, so we would take the average, but you could look at something else, but typically it's the average. Okay. What's interesting to me, at least, is we want to look, so it works better with an unstable prediction method. So what it means to be unstable is that if you change the data set, then all of a sudden your predictions are all off. Okay, so because we're combining these unstable data sets, so then things are going to smooth out, essentially. Okay. So we're going to talk about kind of 3 key ways of getting these unstable methods. Okay, and so the first one is bagging. There's bagging, boosting, and I want to say random forests, but maybe it's in here. Yeah, bagging, boosting, and random forests. I thought there was another one, but anyways. Okay, so if we're bagging, then what we're saying is that in the bagging approach, the base model is going to be generated by first constructing multiple training sets, okay, by repeatedly random sampling from our N observations, okay? And then, but after we've collected one training set, then I put those guys back in the pond, and then I can randomly sample them again with replacement, okay? And so, so there's with replacement. And because there's replacement, some of these observations that I have, I mean, in theory, they could be in every training set, right? One observation could be in every training set. Highly unlikely, but it's possible, right? There's some probability of that happening. And also there's the possibility of some observation doesn't appear in any of the training data. But overall, we have these many training sets that we can apply these models to, and then we can compile the results, and then our prediction is going to be kind of the meltdown of all those training sets. Yeah. Let's see here. So if we're doing classification and we're bagging, then let's say that we have 10 training sets. Training sets, right? 10 randomly selected training sets with replacement. Okay, and so we've got their age, and then we've got their lone default information. And for tree number 1, it predicted it was going to be a 0 and 0, 0, 0, 1, 1, 1. And we've recorded the overall error rate for each of these trees. Now, what we do if we are bagging these classifications, right? Or using an ensemble method of bagging, then what we do is we take the number of ones, right? And say 1, 2, 3, 4 out of the 10 predicted to be ones. Okay, so 4 out of 10 predicted to be ones. And so the average vote is 0.4. So then if it's less than 0.5, then we classify it as a 0. If it's more than 0.5, then we classify it as a 1, right? So the same cutoff value. But what's nice is that the overall error rate of 20% is decreased from the individual error rates. Okay, so that's the reason that we would consider more and more trees, because if we consider them all together, then we're able to build a better prediction, right? Better models. One kind of fun idea is instead of using separate validation sets, so if instead of pulling out a validation, so first we pull out a test set, that's normal. Instead of pulling out a separate validation set and then picking our training set from there, what we can do is we can say, okay, well, for each training set that I build, there's going to be some observations left over. How about I make that my training set? So they're out of the bag and the training set is in the bag, right? You put your training set in the bag each time. And then the ones that are out of the bag, we use as our validation set. So then we apply our model to that validation set. What that looks like when we get it here. Get it. What happens though is some of these, not all the observations are going to be in every single validation set, right? We're going to have a compilation of validation sets as well, right? And so here are our observations, and these, there are going to be 3 observations missing, I guess, or 2. 1, 2. Seems weird that there's a different number of observations missing, doesn't matter. And so then we can use that as our validation model, right? And so here we've got our votes. If there was only one for this observation, and if one model predicted that it was going to be a 1, then of course we classify it as a 1. Okay. And if there's kind of a tie, then we need to decide if we classify it as a 0 or a 1. We use 0.5 as our cutoff again. A little bit more sophisticated than bagging is boosting. Okay. So it does generate multiple training sets, okay? But what happens is we start off and it's the same as bagging, okay? You generate your first training set. And then what you do is you build your training set, and then you see what your classification error is for a classification situation, which is easier to think about. Right. And then what we do is the observations that we have a hard time predicting, right? So if there's an observation that we're predicting incorrectly, then we boost that observation, right? We kind of, we give it a higher weight for being picked for the next training set. The reason we do that is because we want to be able to pick up on those things that we got wrong, those observations that we predicted incorrectly. We want to boost them in our next training set so that we can learn from them, right? And so with each training set, it depends on what happened in the previous training set. And then the ones that we correctly classified, we can down boost those, I guess we can downgrade them and give them a lower weight. We don't need to work so hard at predicting those because they had features that were easily detectable, and we could predict them correctly right off the bat, right? And so we don't need to worry about those so much. And then so we keep boosting those observations that were incorrectly classifying. And then our final model does something similar. So where the where the classification error is low, we boost those results, right? So we boost those predictions and we give them a higher weight than for the models where our classification error was high. We don't want to include those so much in our model. We do have them in there, but we don't want to have them as prominently as the ones that we're predicting really well consistently, right? And so, so we get this kind of, it gets tricky, right? Because the next training set depends on the previous training set. What happened in the previous training set that I can learn from, and which ones do I boost and which ones do I downplay? And so it becomes this iterative approach, which is computationally expensive, right? But it does give us better predictions. Okay. I'm not gonna, everything I said is all in here. I can't remember. There was something I wanted to highlight, but I think we'll just talk about it. The last method is random forests, which it's really cute, right? Because we made a tree, and now if we make multiple trees, we have a forest, okay? So a random forest generates multiple training sets, and maybe I didn't highlight the boosting differs from bagging. Boosting iteratively adapts how it samples when constructing an blah, 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 blah. Here, I'll just highlight what I said, just so you have it there. Okay, but that's what I wanted to do here. That's what brought me there. Okay, so random forests are the same thing, but now we're making these classification trees, and instead of just having one that we follow, then we make tons of trees. Okay, but what we do is each tree is restricted to only using a fixed number of randomly selected, so these are all randomly selected input variables. So what we say is, okay, for this model, this tree, you're only going to look at these 2 variables, for example, right? And let's say we have 6 variables to choose from, or maybe even more, 10 variables, 14, whatever, 54 maybe. So depending on how many variables you have, you'll restrict it to a smaller subset. And so, so each tree is going to use potentially a different subset of input variables. Okay, so each tree will use a different subset of input variables. Okay. So if we have M training sets, then we establish those splitting rules and for each of those trees. Okay. And so what we say, so the individual classification trees, we call them weak learners because they're only allowed to look at that small subset of variables, right? But then when we combine them all into an ensemble, right? Then what we're doing is we're reducing that probability of overfitting because now we're looking at this group all together. So there's no need for pruning, which is nice. But we just consider all these trees at the same time and just kind of look at the group of them together. Okay. So it's not unusual for random forests to have hundreds or even thousands of individual trees. This is not something you'd want to do by hand. You'd get some computer to just run these for you and generate these trees and then put them together in some sort of way. I'm being vague because usually it's the average, but you'd put them together. And then you'd consider their overall prediction. And then to wrap it all up, I found the cute sticky note. Why not? Okay. So here, I just wanted to summarize that the predictive performance of boosting is going to be better than just bagging. Okay, but what we said was that boosting is more expensive if you're running computers all the time, right? Or if you don't have a computer, then very expensive. Right, and so, and it's because it iterates over the previous training set, right? And kind of figures out who gets what weight and then goes from there. Okay, I see that I kind of used up that time. I do want to just quickly show you how to run some logistic regression in R. I posted that PDF, but I'm not even going to celebrate the fact that this concludes the material for the course. Good job. But also, please stay on the line. So here's the PDF that I posted. This is just a quick summary of that video that I posted from Friday. So if you haven't watched it, then you'd have to watch that first. Okay. But then what I wanted to show you is this example. Okay. Example of logistic regression. Okay. If you haven't watched that video yet, this will make no sense. So, but what we're going to look at is some possum data. So in Australia, there are these cute possums, and I went through this in my other class yesterday, and I found the image of these guys. Hey. Here's the possum that we're talking about. Okay, and so what we have is we have 104 of these possums, and we've measured things like their head length, their skull width, their total length, and their tail length. Oh, sorry, I missed the gender. The sex male is an indicator. And what we're trying to figure out is if they're from Victoria, the Victoria region, or if they're from the New South Wales and Queensland region, which we denote as other. So we've got this binary outcome for the pup. Binary outcome, we let 1 be Victoria, 0 be other. Okay. And we're trying to predict, so if we have information on the gender, the age, more likely dependent on the head length, the skull width, and the total length, and the tail length. Okay, so if we have information on all that, then can we correctly classify if they came from the Victoria region or the other region? Okay, and so, whoops. I looked at the names here because these are the variable names that we're using. And then I'm not going to copy that in, but then I looked at, okay, so there were 46 possums in the Victoria region and 58 that were actually from the other region. So these are the values that we would compare our predictions to, right? Our predicted classifications, we can compare them to what actually happened. So first thing I'm going to do is I recoded because it's coded as text, so Vic or other. So what I started off doing was I recoded using an if-else statement. So if the possum pop is equal to, because remember, if you use the if-else statement, it has to be a logical statement. And so if it's equal to Vic, then give me a 1 in this new column called pop dummy. So then give me a 1, else give me a 0, right? And then that way I'll be able to have a new column here on the side called pop dummy, because I don't want to overwrite the pop column. I can add on another column here called pop dummy and use that with the 0s and 1s. And then I can retain this information, the text information, if I need it for a different scenario, right? So if I make a plot of the pop dummy against the tail length, I just picked that arbitrarily. Selected arbitrarily. Somewhat. I was looking for a plot where the dots weren't all on top of each other like this, but where there was some sort of shift, because those are the interesting cases. Okay, so when I plotted that, I get a plot that looks like this. Okay. So I was looking for kind of a shift in these 0s and 1s. So remember, the dummy variable, it's either 0 or it's 1, and then I've got the tail length here. Of course, I haven't cleaned up my plots. This is just exploratory work. Okay. So let's see if I can grab all of this here. Let's see here. There. So I'm first going to look at the relationship between pop dummy and the tail length. I'm focusing on one explanatory variable or one predictor variable, because that way I can plot it on the graph and we can still see it. As soon as I have more than 3 variables, it becomes impossible to visualize. And so here I want to focus on one to show you what happens. And then, of course, we can extend it, but we can't visualize it anymore reasonably. So what we do is I'm going to focus on, if I want to predict the probability of being in class 1, if the tail length is 36 inches. The reason I picked the 36 inches is from the data set here, right? The first observation has a tail length of 36. So what I want to do is I want to find the predicted value for the 36 tail length and then compare it to what actually happened in the data. Am I going to classify it as a 1 or am I going to classify it as a 0? It is a 1, right? But depending on my model, I might classify it as a 0, right? Given the tail length. So what we're going to do, right, is we're going to use the GLM command, okay, or the GLM function. So the generalized linear model function, you tell it to use the GLM command by just using GLM. You've seen the LM command, and so now you use the GLM command, and by saying family equals binomial, you're telling it you have a binary outcome, right? And so that's how we force it to be a logistic regression. Okay? The setup for the GLM is exactly the same, except you add the family equals binomial. So you do your pop dummy against the tail length. Okay, so you do your dummy variable that you're trying to predict against whatever predictor you want to include, looking at 1 to start the data set and You have to have that family equals binomial, otherwise it won't know what to do. I'm going to call it log mod because I'm going to create lots of models here, or a few models at least. So I want to have distinct names for all of them. So if I call it log mod and I run the summary of log mod, Cable wasn't working on this summary command, so I'd have to look into it, but that's okay. It's nice to see the summary as it comes. Okay, so what we get is we get the logistic regression coefficients are 25.5662 and negative 0.6996. Okay. Down here, we get the AIC. Okay. We select, because I didn't mention this before, but we select the model that minimizes the AIC. Okay, it's much like the R squared in a regression context, right? Because you want to maximize your R squared, and now here you want to minimize your AIC, and we're going to use the AIC for determining the performance of each model. And just remember, you want to minimize the AIC. Okay? So what this is saying is it's saying that the ln of p hat over 1 minus p hat is 25.5662 minus 0.6996 times the tail length. Okay. But we want the predicted probability, right? So what we can do is we can substitute the tail length of 36 and I'm going to get the ln of p hat over 1 minus p hat is, now I can't remember what it is, 36 times 0.6996, negative of that, plus 25.5662. I get 0.3806. This is the same as B0 plus B1X. So now what we can do is we can take that we developed in the video, and if you haven't watched it, then, well, that would be hard. Solve for P hat. P hat, oops, is the predicted probability. And it's going to be 1 over 1 plus E to the B0 plus B1X. Sorry, negative that, which is 1 over 1 plus E to the negative 0.3806. So negative of that, and then E to the power of that, 1 plus that, 1 divided by that. I get a probability of 0.5940178075. Okay. We solved for p hat by hand, but we can confirm it using the predict function, and the predict function takes a model. Okay. And it generates some p hat. So it takes a model, it knows we have to give it the data set to apply it to. And then the type that we want to predict is the response. And so then we add it as a new column called p hat to possum. And here we have our predicted values. Notice that these are slightly different, but that's because we used rounded values for the coefficients. Slightly different because we had to use rounded coefficients. Okay. And I know I'm plumb out of time. And if you have to go, that's totally fine. But I do want to finish talking about it. Hopefully that's okay. But I do understand if you have to go, so don't worry about that. But it'll be in the rest of the video. How about that? Okay. So if we plot these probabilities, remember we're expecting to see that nice S shape. But when we look at this graph that I've included here, right, this doesn't look very nice at all. So what I'm doing here is I'm going to plot the pop dummy against the tail length for the possum data. And then what I want to do is I want to add lines for p hat against the tail length, because the p hat is going to give me that, or ideally going to give me that nice curve right here. I was expecting an S curve. I'll say expecting. I'm showing you this because this is not what you want, but it's what would happen. So I'm going to show you how to fix it. Okay. So you can add the lines and notice that it doesn't give us that smooth curve. So to add that smooth curve, what we're actually going to do is we're going to add a series of points. So a lot of points. So we create fake X values that are close together. And what we're going to do is we're going to force them to range from 32 to 43. Okay. And so, of course, we reference the data, but what we're going to do is we're going to create this new data. New data is going to be a data frame. And it's going to have a column called tail length, which is going to be a sequence from the minimum tail length in the possum data set to the maximum tail length in the possum data set. And I want 500 evenly spaced points. Okay. So then I'm going to create a pop variable for the new data. And this is going to be, these are going to be the predicted values of the pop. Okay. And so if I use the predict function again, I'm going to use my log mod, that same model that I had. I'm now applying it to the new data. And remember, our model was using tail length as its variable. Now, new data has one column and it's called tail length. So we're good to go. Okay. And so now what we're going to do is we're going to predict the responses given those 500 tail lengths. Okay. And then I'm going to store those in a new column on new data called pop. Okay. And so what I can do is now I can make that same plot of the pop dummy against the tail length for the possum data. And then what I do instead is I add the lines not from the possum data, but I add it from the new data, which has 500 nicely spaced, just a sequence of 500 points between 32 and 43. And when I plot that, then I get, where is it? I get this beautiful graph. How nice is that? Okay. I also added a horizontal AB line or AB line at 0.5 because that's my cutoff value. Oops. Cutoff value. So at this point, and maybe I'll do this. So from here, they're in class 1. they're classified as class 1. And then from here, they're going to be classified as class 0. Some of these are misclassified, or sorry, some of these are misclassified on either end, right? But it captures the majority of them, right? So it's a trade-off. Okay, so our goal is to classify these observations. So what we can do is if we use these, hey, do I have these? I wanted the table. Oh my gosh. I wanted this table, right? So if I have a p hat that's more than 0.5, then I classify it as group 1, right? If I have a p hat that's less than 0.5, then I classify it as a class 0, right? And so I can use these p hats to figure out who's in class. So the predicted class be class 1, class 1, class 0, class 0, class 1, class 1, etc. Right? And so some of these are going to be incorrect, right? Because all of these we can see should be class 1, but we would classify this one correctly, this one correctly, this one correctly, and this one incorrectly. And these two would be incorrectly classified, right? So from here, you can build your confusion matrix and you can figure out your misclassification rates, right? Class 1 errors and class 0 errors. Yeah. The last thing I want to do is just have a look at what if we have more than one predictor. Okay. So what if we have something like this? Oh, and I guess there's a little bit missing here. Gonna grab it. There's more to this example later, but this is where I'll end it. Okay, so here I can add more predictor variables the same way that I did for the linear model, right? And so I have the same setup, but now I just add, and I am literally adding them, add the predictors in my model. And then I'm going to see that some of these predictors are not contributing to the model. So I would remove them one by one and refit the model. And if, you know, with every change that I make, there's going to be changes in the p-values. So they're not stationary. They depend on what else is in the model. So I would first remove the age variable because it seems to have nothing to do with predicting the region, which makes sense, right? And so I would remove that from my model. And what I would do, I would land on the model with the lowest AIC, or the models with the lowest AIC. So this is lower than what we saw initially. So this is a better fitting model than we had before because we've incorporated more information. But there's some redundant information in here that we don't need, right? The age variable, we would remove first, and then we would refit it, and then we'd keep going until we have our best model. Okay, where we're looking for all significant coefficients. Okay. Okay, let me just go back to this example. I also introduce an interaction term here, but you guys don't have to use the interaction term. It's okay if you want to, but you don't have to do it. So I'm going to skip it. And that's it. Okay. So if you have any questions, let me know. Otherwise, I see you on, well, I'll send out an announcement potentially on Monday, or if everyone's okay with me just posting a run through video, then I'll do that. And then I'll see you maybe on the 13th for some questions about the final project. Okay, have a great weekend and see you on the 13th.